A combination is when you are asked to choose R objects out of N objects that you're given and arrange them. The order in which you arrange them doesn't matter. Now, obviously, R is going to be smaller than N. I can't say to you, choose 9 objects out of 3 objects. That wouldn't make any sense. So R is always going to be smaller than N. Let's look at an example so that you can understand what I mean by saying their order doesn't matter. So let's look at this example. You have 6 pairs of distinct socks in your drawer. In how many different ways can you pick 3 to put in your suitcase? Well, let's first understand what it means by 6 pairs of distinct socks, because the fact that it's distinct is important. What that means is you have 6 different pairs. So let's say we've got a red pair, we'll call it R, an orange pair, a yellow, a green, a blue, and a violet pair, each from the color of the rainbow. So those are the 6 distinct pairs, and we want to pick 3 to put in our suitcase. Well, the question is, if I pick the red, and then the orange, and then the blue, is that any different than choosing the blue, the orange, and the red? Is there any difference here in the choices? And the answer is no. It's all getting dumped into your suitcase. The order doesn't matter in which you pick those. So that's what we mean when we say order doesn't matter. Here's another example. You bring home 5 new books from the library. In how many different ways can you choose 3 to lend to your sister? Again, let's assume that those books are, we'll just give them numbers, 1, 2, 3, 4, and 5. If I pick 3, 4, and 5 to lend to my sister, that's exactly the same as my choosing 4, 3, and 5 to lend to her. So there's no difference here. These are the same choice. And that's what it means by the order doesn't matter. If I had said put them on a row on the bookshelf, that would be different, because then 3, 4, 5 and 4, 3, 5 would be different orders. That would be a permutation, but that's not what we're talking about in this problem. So the first thing you should ask yourself when approaching a combination problem or any counting problem is, does the order matter? So let's take a look at our formula. We have Cn of R, that would be n objects taken R at a time, so we're choosing R from the n objects, is equal to n factorial over R factorial times n minus R factorial. You will notice, if you've studied permutations already, that this looks an awful lot like the permutation formula. The only difference is this R factorial here. Without it, it is exactly the permutation formula. So what we're doing by dividing by R factorial is we are eliminating all of the repetitions. The idea is that you do not want to count ABC as well as BAC or CBA, for example. You don't want to count all of those individually because the order doesn't matter. They're all the same. So the dividing by the R factorial says we're going to get rid of all of those repetitions and only count the unique representations of what we're looking for. So this is our formula. Another way to think about this really is just, this is the same thing as the permutation divided by R factorial. That's exactly what it says. So let's just do a quick example and see how it works. So let's say we have 6 objects like we had at the beginning. We had our socks and we want to choose 3 of them. So in that example, n is 6 and R is 3. So we're choosing 3 socks out of the 6. So our formula looks like C of 6, 3 is 6 factorial over 3 factorial, that's my R, divided by 6 minus 3 factorial. So this is the same as 6 factorial over 3 factorial, 3 factorial. We can write that out just to show what's going on. 2, 1 over 3, 2, 1 times 3, 2, 1. Now notice these cross off. And actually, I can also reduce, if I want, the 3 times the 2 is 6. So I can actually eliminate that and my answer is just 20. So you need to practice working with the formula, but it's pretty straightforward as plugging in N and R.